Now we reach the main operation of this chapter, append. We add one value at the end. Let's start with the easy case, then the hard one. First, the easy case. When size is less than capacity, there is spare room. The slot at index size is free. We do this in 3 small steps. Highlight the slot, write the value, then raise the size. Step 1. Size is 4, so index 4 is the first free slot. Nothing is written yet. We just point at the slot where the new value will go. Step 2. We write the value 9 into index 4. Only that one cell changes. The size is still 4 for this instant. Step 3. Now we raise the size from 4 to 5. That is a separate step. One write, no copy, no resize. The cost is big, O of 1. So append with room is big, O of 1. One write, one counter bump, and capacity is untouched. The interesting case is when the buffer is full. Now the hard case. When size equals capacity, there is no blank slot left, so append cannot just write. It must make room first. Let's predict together. The buffer is full at capacity 4. We append one more value. What grows and how many elements get copied? Hold your answer for a moment. And the answer is this. We grow to capacity 8. We copy the 4 live elements. Then we write the new value. Let's watch a resize on a memory map. Here is the start. The old block at address 5000 is full. It holds 4 values at index 0 to 3. The data field holds 5000. That is the address of the old block. Size and capacity are both 4, so there is no free slot. Step 1. Allocate. We ask the heap for a new block 2 times bigger with room for 8. It sits at a new address, 9000. Step 2. Copy. We copy the 4 values into the new block, one at a time. This copy is the big O of N part, the slow work. For now, data still points at the old block. Then we write the new value, 5, into slot 4, at address 9016. Step 3. Repoint. We point the data field at the new block. It now holds 9000. Growth changed 2 fields, not 1. The capacity is now 8, and the data field now holds 9000. The header itself never moved. It stays at 2000. The write raised size to 5. Last, we free the old block at 5000. Its 4 values are crossed out here. That memory is gone. Any old pointer into it now dangles, so we must not use it. Remember this. The data field is a pointer. It stores the address of the block, now 9000. It is not the block itself. Let's name the 4 steps in order. First, ask for a larger block. Second, copy the live elements over. Third, repoint the data field at the new block. Fourth, write the new value and add one to size. So here is the rule. A full buffer resizes first, then writes. A buffer with room writes right away. The copy is the slow part, and doubling makes that copy rare. One more warning. The new block sits at a different address, so the data field must be repointed to it. Any old pointer into the buffer is now dangling. Now let's watch the resize happen, one change at a time. We start full at capacity 4, and we append the value 5. Each row is one small change, and the rows stay so you can watch the new block fill. Here is the start. The old block at address 5000 is full. Size equals capacity, both 4. There is no room, so we must grow. Step 1. We ask the heap for a new block 2 times bigger with room for 8. It sits at a new address, 9000, and every slot is empty. Step 2. We copy element 0, the value 3, into the new block. One element only. Step 3. We copy element 1, the value 1, into the new block. Step 4. We copy element 2, the value 4. Step 5. We copy element 3, the last value, another 1. Now all 4 elements are in the new block. The 4 elements are now copied into the new block. Now we finish the append, still one change at a time. Step 6. We repoint the data field to the new block at 9000. This is its own step. Step 7. We update capacity from 4 to 8. Step 8. We free the old block at 5000. Its memory goes back. Any old pointer into it is now dangling. Step 9. Now there is room. We write the value 5 into slot 4. Step 10. Last, we raise the size from 4 to 5. The append is done. Notice the block moved to a new address, so we never keep a raw pointer across an append. So remember this. After the resize, only the data field is valid. Any raw pointer someone still holds into the old block is now dangling. Never keep a pointer into a dynamic array across an append. Let's look at the shape of the append function. The rule is small. We grow the buffer first, but only when it is full. Everything else is just one right at the end. This line asks one question. Is V arrow size equal to V arrow capacity? That means every slot is used. There is no spare room left. If the buffer is full, we call grow to double capacity. This makes the block twice as big. It returns a status. A non-zero result means the grow failed. Remember, the block may also move in memory. Here we handle that failure. If the grow returns non-zero, we stop and return -1. We do not ignore it. The vector is left whole and safe. When there is room, we write x into V arrow data at index V arrow size. That is the first free slot, right at the end. Then, as a separate step, we add one to V arrow size. The array is now one element longer. When the buffer is not full, only the last 2 lines run. One right and 1 plus 1. That is the whole cost of a normal append. It is big O of 1. And if the grow ever fails, we bail out with -1. Now let's see the real C. The key tool is realloc. It does 3 jobs in one call. It allocates a bigger block, copies the old elements over, and frees the old block. But the block may move, so we must be careful. First, we pick the new capacity. If the old capacity is not 0, we make it capacity times 2. That is doubling. If the array is brand new and capacity is 0, we start with 1. Now we call realloc and save the result in a temporary pointer called TMP. We do not write it into V arrow data yet. Remember, the block may move to a new address. This is the safety check. If TMP is null, realloc failed. There was not enough memory. We return -1. The old block is still there, safe and whole. Only when TMP is good do we point V arrow data at it. We repoint the handle just on success, and then update the capacity. This line is the common case. Most of the time the buffer is not full, so we skip the whole grow step. We write x into the slot at index size. Then in a separate step, we add 1 to size. The whole append is big, O of 1 amortized, because the grow branch is rare. It is not just this one line that is cheap. It is the append as a whole. Now the trap to avoid. Always save realloc's result in a temporary pointer first. If you write V arrow data equals realloc of V arrow data and realloc returns null, you lose the old block. That is a leak. We look at this classic bug again later. And remember the cost. The whole append is big O of 1 amortized. The grow branch is rare, so the common cost is just the last 2 lines, the right then adding 1 to size.